Professor Utonium is using chemical X in his next experiment. This radioactive material decays at a rate proportional to the mass of the chemical present. Professor Utonium received a batch of 1,000 grams, or 1 kilogram, of chemical X and put it in storage. 2 days later, he finds he has 810 grams left, so some of it has decayed. Create a differential equation to model the decay rate of chemical X and determine how much of the substance the professor will have the next day. Okay. So, 1,000 grams when he gets it, then after 2 days, 810, then after 1 more day, so that's 3 days since he got it, we want to know how much. And we're going to use a differential equation to do this, because we're talking about chemicals, radioactivity, isotopes, we're talking about decay rates. Okay, this is radioactive decay, which has a very particular style of differential equation. So we could let, well, usually I use m for mass, but I'm going to, in honor of chemical X, say x of t is the amount of chemical X. The question just mentions days, so we'll say amount of chemical X in after t days. Okay. Now we're told how the material decays. It's got a rate of change that is proportional to the amount of material present and the amount of chemical X we've got. So there's our differential equation, and now it's up to us to solve it. Okay, so what should we do? What would be a good differential equation in this situation? Or a good differential equation technique? Okay. We could treat this as a linear differential equation. Okay. So we could subtract k xt and get 0. We're almost there. This isn't in standard form. Okay, we'll put a minus k there. Okay, and this plus sign is important for our technique for linear differential equations. So now we need an integrating factor, which is going to be e to the power of this function being multiplied by x of t. So minus k, it's a constant, but it's a constant function. So we need e to the power of some antiderivative of this minus k. So e to the minus kt will work just fantastically. So that's our integrating factor. So we come along and we multiply everything, multiply both sides of the equation by our integrating factor. Okay. Now 0 times anything is 0, and the nice thing about this is the left-hand side is really just the expanded form, using the product rule, of the derivative of the integrating factor times our function, our mass of chemical X. Okay, so x of t. Now, the integrating factor, what did we just say? It was minus kt, e to the minus kt. If we integrate both sides, okay, we can start to solve and isolate for x of t. Now, the antiderivatives of 0, well, only the constant functions have a derivative of 0, so there's some c out there that should make this work. And if we multiply both sides by e to the kt, or divide both sides by e to the minus kt, same result either way, we will get an expression for our function. But we don't know what k is, and we don't know what c is. Okay, these are things we have to work out. But we have information. Okay, after 0 days, that is when Professor Utonium gets his chemical X, he's got 1,000 grams. 2 days later, he checks his storage, and he finds he only has 810 grams. Okay, these two pieces of information can let us figure out c, the constant that came from our integration, and k, our proportionality constant, which is based on the chemical X's properties. Okay, so we've got 1,000 is equal to, what do we say, c e to the k t, but in this case t is 0. So that's just going to be c e to the 0, c times 1, c. So C is 1,000. Okay, now we know 810 grams is X at 2. C we know is 1,000. So e to the k times 2, so e to the 2k now. Okay, and we can use this to figure out what k is. Divide both sides by 1,000. We get 81 over 100 is e to the 2k. Now we could go about this by applying logarithms to both sides, and that's perfectly fine. That's natural. It's typically what we do. But I just noticed 81 and 100 are both squares. So I'm going to bring the 2 out here, and we're going to square root both sides. Okay, so e to the k must be the square root of 81 over 100. Now e to the anything is always positive. That's why we're not messing about with this plus minus stuff. Okay. The square root of 81 is 9. And the square root of 100 is 10. So e to the k is 9/10. That actually is enough to express the function that we want, but we could go further if we actually want to solve for k, or if somebody specifically asked, we just do ln of both sides. Okay, ln of 9/10. Another way of writing that is ln 9 minus ln 10. Okay, whatever you need to for your k value. Okay. So we can get our function. We're not actually interested in the specific function. We want to know how much is left after t equals 3 days. Okay. So x of t is going to be 1,000 e to the k, so e to the ln 9/10 t, which you could, if you want to, rewrite as 1,000 9 times 9/10 to the t. You can absolutely do that. I'll leave you to do that on your own, and I will proceed without doing that. But I think it makes the numbers a little bit nicer. Anyways, let's continue on. We want x at 3. So 1,000 e to the ln 9/10 times 3. Bring the 3 out. We get 1,000 e to the, and ln of cancel out. Okay, and then 9 to the power of 3 is 729. So 9 squared is 81 times another 9, 729. And then 10,000 on the bottom gets cubed as well. Look at that, the thousands cancel out. So after 3 days, Professor Utonium should have 729 grams left of chemical X.